Okay, so hello everyone. Nice to see you all here. My name's Sarah Barber. In case you don't know me, I lead the Wind Energy Innovation Division at the Eastern Switzerland University of Applied Sciences. I also lead the Swiss Wind Energy R&D Network, and I'm really happy today because this is a first time. So this is the first webinar of our new IEA Wind Task 43 Metadata Challenge webinar series, and we've got Jean-Paul here from the Western Switzerland University to talk about ontology-based techniques for managing data streams. And so as I just was saying before I started recording, well, the plan is basically here, and I think we've probably got enough time because we're a small group for everyone just to quickly say hi, if they don't mind. If you do mind, then please feel free not to. I'll just go around the faces that I can see on the screen, and Yuri happens to be the first one. I think you can just speak without turning your microphone on, can't you? If everyone just wants to quickly say hi, where you come from, and maybe why you're here, just very briefly, and then we can continue. Go on, Yuri.
Okay, so I'm Yuri. I'm a PhD student working with Sarah as my supervisor on digital twins. And yeah, digital twins are not about models. Models are not just about data, and data is just not about ones and zeros. So that is why we're talking about meaning and ontologies and understanding. So I hope everyone enjoys the webinar series.
Cool, thank you. Jean-Paul, I'll skip over you because you're going to introduce yourself in a minute anyway, I guess. So you can say hi as well. Colin, you say hi as well. I don't want to leave you out.
Hi, Jean-Paul from HES-SO University of Applied Sciences, Western Switzerland. So I speak to you in a bit.
All right, Stephen.
Hi, I'm Stephen Halloran from Brightwind, based in Ireland. We do wind resource assessments for pre-construction wind farms and operational assessments as well. I'm involved with Task 43 wind digitalization, specifically the wind resource assessment data model that we created.
All right, thank you. Marcus?
Hi guys, I'm Marcus. I'm from Fraunhofer IWIS. I'm working on digital twins as well and try to use ontologies for interface management. And yeah, that's why I'm here today, to learn more about ontologies.
Great, thank you. Christian?
Hi, I'm Chris. I'm working for technical consultancy Natural Power, based at home in the south of Germany. And I'm involved with a lot of different kinds of modeling and analysis work for wind energy, and kind of increasingly focusing on developing software for modeling and analysis for internal use.
All right, thank you. Lewis?
Hi everyone, I'm located also in Germany, in the northern part. I work for DNB, and well, I'm working mainly on operational energy assessments, wharf modeling, I think climate modeling. Yeah, I have to deal with big data for solving some problems. It's the first time that I joined this meeting, and I just heard this week about Widow Wind. Yeah, I'm just curious to see, to know you better, to know, yeah, what are the challenges that you are facing on, and I'm very curious about it. So
all right.
Thank you for having me.
Great, thank you. Vaiva, is your connection good enough to speak?
Yeah, I hope so, because I'm in the train. But hi, I'm Vaiva. I'm sorry that I cannot have my camera on, but I'm afraid that it will break. So I was very nicely invited to this meeting by Sarah, and thank you very much. I'm the analyst for digitalization and cybersecurity at Wind Europe in Brussels, and currently I'm traveling to north of Europe. And we are also working, I'm the project coordinator of the project WEDS. This is internal project of Wind Europe members. That is wind energy data standards, and we are looking for the probability and hopefully of creating a universal wind data standard. So I'm very interested to know more about what they're doing and the ontologies of data as well. Thank you.
All right, great.
I hope you heard me, actually. I don't know.
We heard you fine, yes. Perfectly, thank you. Okay, Philip?
Yeah, just turn my camera on quickly. Hi, yeah, I'm Philip Bradstock from BitBloom, and we do mainly software and consultancy for post-construction analysis. So things like performance monitoring and condition monitoring of operational turbines. Yeah, I guess at this stage I'm just here purely out of curiosity, let's say.
All right, nice to see you. Sometimes I see all these names on these Excel sheets where people signed up and I don't know who anyone is, so it's actually nice to see faces to names. Okay, Riyad's just left. Okay, Riyad was actually just driving and I was slightly concerned by that, so maybe he's just arrived at his house or something. But anyway, okay, so let's move on to the schedule for today then. I've just got like 2 slides about what the metadata challenge is, and then I'll pass over to Jean-Paul. And yeah, the idea is that he talks for about 20 minutes and then we have a Q&A. You can see there's a mistake on the agenda. We've got 5 minutes of nothing, apparently. But it would be nice if we could, as well as having a Q&A, have a little discussion about what this all means for wind energy and for sort of the overall goals of the metadata challenge, if we have time. So just quickly, what is the IEA Wind Task 43 metadata challenge? So IEA Wind Task 43 itself is actually part of this thing called IEA Wind TCP, which is technology collaboration program. There's lots and lots, as you can see by the number 43, there's about 50 of them. Different collaborations where people meet and try to align their research interests. And Task 43 is called Wind Energy Digitalization. And you can find much more about the task on this website here. I'll put it in the chat afterwards. And the metadata challenge kind of is part of the task 43, or part of this work package 2, which is called Data Standards and Sharing. And we started the challenge in order to sort of we called it a challenge because we wanted to have some more fixed goals and be a bit more goal oriented about what we were doing. But actually it turned out that the goal of the challenge has become to research into metadata and knowledge engineering for wind energy applications and use the results to develop recommendations for the sector. And we divided it into 4 sub-challenges, which are led by different people. So we have one about managing metadata and schema. We have one about defining schema for data and metadata. We have one about existing works and community. We have one about, well, it's more like about politics and communication. And so as part of Challenge D, we actually recently decided to launch this webinar series because we're a closed group. So to take part in the metadata challenge, you have to sign up. You don't have to pay anything and it's free to everybody, but you sign up on the We Do Wind platform. It's one of the spaces of We Do Wind, and that just gives you access to the digital platform that we use to communicate, and it gives you the invitation to the meetings. And we have monthly meetings where we discuss all these 4 things. But we decided we want to have a public webinar series where anybody can just sign up for one webinar if they're interested, to try to get the conversation, let's say, between the hardcore wind energy people and the rest of the world. So this is what we're doing now. Just a quick note about what We Do Wind is, just because somebody mentioned it already and I don't have it on my slides. Like the We Do Wind project is just trying to improve data sharing and collaboration in wind energy in general. So as part of Task 43, we actually discovered that lack of data sharing, or let's say a fear of data sharing, is one of the largest barriers to wind energy digitalization. And the idea of We Do Wind is that we make like a mutually beneficial win-win situation for people. So there are lots of wind farm operators, for example, who have lots of data and they're looking for the most state-of-the-art best techniques to analyze the data. And on the other hand, we've got a load of researchers who are doing a load of state-of-the-art analysis, but they're desperate for data. So the idea of We Do Wind is to bring these 2 parties together and actually say, okay, if you share some data, you actually get a benefit, you actually get connection to this community. And so we've had a few challenges. We've had the EDP challenge, we've had the WindG challenge, WindG is a Swiss company. We're running a few other ones. We've had one from Cubico, which we've just launched, and one from UDing from the University in Texas, and some of you here are involved in those as well. And yeah, the the metadata challenge is just one of the things going on in that We Do Wind space. So I'll put the link for We Do Wind in the chat as well. Why is knowledge engineering important? I'm glad you said what you said, Yuri, because it kind of just agrees with what I've written here. So the successful digitalization of wind energy is one of the key drivers for reducing costs and risks over the whole cycle. There's quite a few different studies showing that.
Sorry.
And some Hello?
Yes. Yeah, I can speak right now because I had a phone call and the connection cut off.
All right, okay.
But now, yeah. Yes,
Okay.
can I represent myself?
You can
Sorry
do,
for,
but you can do,
okay.
yeah. But can you just wait until I'm finished speaking? Like I'll
Oh.
pass over to Jean-Paul in a minute, and I'll ask you to introduce yourself when I do that. Is that okay?
Okay, no problem. You can
All right.
continue. No problem. Sorry for
Thank you.
interruption.
Okay, no problem. So there's some opportunity. I mean, digitalization offers lots of opportunities, and they include things like digital twins, predictive maintenance, drones, AI systems, and all these type of things can contribute to reducing the maintenance costs, increasing the amount of energy delivered. But as Yuri very nicely said, like, in order to do that, we don't just need physics, simulations, and analytics. We actually also need, first of all, we need systems or AI systems to process, interpret, perform logical operations on structured data, which we call knowledge engineering. But we also need this structured data that represent the information so that it can be used by these systems, which is called knowledge representation. And what does it mean, improving our understanding of knowledge engineering? Well, first of all, it kind of means, what do all these terms mean that people are using? So we kind of established in the metadata challenge, but also in IEA Task 43, there are all these words that people are using: metadata, taxonomy, ontology, schema, knowledge-based, and they're not actually that clear and obvious. So we tried to, well, we've created a glossary. I can put the link in the chat as well. And it's a document which is developing as we go along, and there's no right answer, but we're trying to agree on these terms so that we can actually, when we use them, when we're talking about them, that we actually agree on what we're talking about. But one of the other things is trying to communicate to people why this is important. So why do you need to know what ontology is in order to build a digital twin? I mean, one really good example is that I was recently involved in an EU project proposal where 20 people were talking about comparing and using different digital twins, and not a single person thought to talk about data structures or any knowledge base or ontologies or anything. They just wanted to build 20 separate digital twins and hope that they could be compared to each other. And I think it's really important, if we want to continue building these areas, if we want to share with each other and benefit from each other, that we actually understand what all this stuff is useful for. We want to know what's been done before. There has been some really useful stuff been done so far. We need to know that so we can know where to start, that we don't start from the beginning again. We want to know what we can learn from knowledge engineering experts. We want to know what we can learn from other domains. We also want to know how can other domains maybe learn from us, because wind energy is highly interdisciplinary and quite an interesting use case, I think. And then also, how can we work together? So that's what we want to achieve with these webinars. So before I pass over to Jean-Paul, first I'd just like to ask anyone if they've got any questions about what I just said, about what we're doing in general. Feel free, by the way, to put your hand up on the in Teams, or otherwise just turn your microphone on and speak. I don't see anybody,
Well,
so I'm gonna.
For me, it was clear.
Yep. Okay, good.
Clear, yeah. Thanks.
Thank you. Feel free to say that as well. Any reaction is a good reaction. from doing lots of online lectures, I very much appreciate even reactions which are saying yes. So thank you. Riyad, do you want to? So we all did a very quick introduction. If you just want to quickly say who you are, that would be great.
Yes, thank you. My name is Riyad Morina, and I'm from Kosovo. Right now, I'm a teaching assistant at the University of Pristina, Faculty of Mechanical Engineering. And so it's a good pleasure to have you here. And thank you for being here and for your presenting.
Great, thank you. And I'm glad you're not driving anymore.
Yeah, the traffic is jam, and so there'll be time to reach the target. Thank you.
All right. Okay, so Jean-Paul, I'm just going to pass over to you, and yeah, looking forward to your presentation. Thank you. You can still do 20 minutes. I think we've still got time, even though we're a little bit behind. So don't worry.
Okay. So thank you very much. So I'm Jean-Paul Calbimonte. I work at HES-SO Valais-Wallis, so it's the University of Applied Sciences, Western Switzerland. I am also part of the SENS Institute and the Research Center, which is a collaboration with the Schub Hospital of Lausanne. So from this, you will understand that some of the work that I do is related to health. So disclaimer here is that I don't have any background in wind energy research, really, but I have a lot of experience in knowledge engineering, knowledge management, and also ontologies and semantic web work, which I think can be relevant to the metadata challenge and topic that you're working on. So as I told you, I work at HES-SO, which is not the Ost, but the West University of Applied Sciences, and we are in nice places like this, but now to the topic, we're going to talk about two things. So I want to talk first about one specific project, which is the WISER project about GHG assessment. And then I'm going to go more into detail into ontology-based data access and what it means and why it can be useful. So starting with the WISER project. So this is a project that is dealing with one problem, which is now we're talking a lot about climate change, and we're talking a lot about goals regarding decarbonization, so CO2 emissions, reducing them. We have set up goals for 2030, 2050, etc. And in order to get to these goals, we need to measure something. We need to measure emissions of different kinds. And often these emissions are described in a way that it's maybe not transparent. So we get some numbers, but we don't know where these numbers are coming from. So we have problems of trusting the data and the calculations that have been done. And sometimes the data is not even comparable because we have developed an assessment framework or use an assessment framework that is not comparable with another because we are comparing apples and pears and peaches and different kinds of things that are not really the same thing. And also we're using very different data sources. So if you're familiar with the GHG and the CO2 emission calculation process, you have to go to different data sources that come from different places with assumptions that sometimes you don't know. And depending on which data source you use, you can really get to very different results. And integrating these very heterogeneous data sources is not easy because they also come in different formats and with different kinds of semantics behind. So semantic is really the meaning of the data. So with all these problems, we have come up with this project, which is a WISER, where we want to build this ecosystem, a digital ecosystem where we can integrate different data sources about greenhouse gas emissions. And we can also apply different sorts of methodologies for LCA, for life cycle assessment. And in this process, it's not only us, but it's also EMPA, PSI, the ZAV in Zurich, University of St. Gallen, and several implementation partners. So we have ABB, Microsoft. We also have the Swiss Data Center Association and cities. We have the city of Lausanne, the city of Winterthur, and the city of Schaffhausen. So we want to really use we're having these implementation partners who will be able to showcase with some demonstrators that our platform can actually be something useful. So this is a project funded by Innosuisse. And within this project, I am leading a sub-project inside this flagship project, which is the communication interfaces and services of the WISER ecosystem. So what are these interfaces? It's basically an API. So if we want to use all these different data sources, we need some sort of API so that these implementation partners, which are represented by these demonstrators, which may build their own dashboards or other systems, so they can use our resources and access, search, and make queries to all the different data sources that have been structured and that have been integrated using a knowledge graph. So if you see in this part of the screen, in the right part of the screen, then you will see that there is this knowledge graph there. So we have semantic data annotated there. So we have metadata with semantic annotations there. that allows us to integrate very different sources of data. So this is what we're trying to implement in the sub-project 3 in the WISER infrastructure. So if we're talking about metadata, we think about ontologies. So these schemas that provide us a conceptual view of a certain domain. So this is one example of an ontology about LCA. So we have things like activities and activity types. We have flows. So these flows will be related to certain materials or to certain exchanges of resources in order to produce, for example, a product. If I want to fabricate a bicycle, for example, I need certain metals and I think we need certain plastics, and these have certain impact as well in terms of CO2, and then you can add up these emissions in a way that makes sense. So there are different ISOs, so different frameworks in order to do that. And we try to model all this information using this ontology. So this is just one example of an ontology for sustainability. There are different ones. Some are more complicated, so some are simpler. So it's always a very difficult work to come up with ontologies, but it allows us to integrate different data sources. And what we do in the WISER is to create this API where we will have dataset catalog service. So this is really for querying metadata. And this metadata is going to be in the knowledge graph of the WISER. We will also have environmental data services. So this is really to access data about activities and processes and how emissions are related to these processes. Some of this data can also come from the knowledge graph, but it can also come from other APIs. For example, if you're familiar with the LCA environment, there is the EcoInvent API, but there are other data sets that provide you this kind of information, and we can integrate them because we have this kind of common schema, this common ontology that allows us to do that. And furthermore, we have computation services using some APIs in order to do calculations. And everything is exposed as a REST endpoint so that external applications can access this. So this is the general architecture of the system. But as you can see, there is this assumption that we can use these ontologies as an entry point in order to get the data integrated. And this is something that looks nice in an architecture diagram, but it's actually very difficult to put in place. And this is perhaps something I will spend more time describing in the rest of the presentation. And this comes to the fact, then I change a bit going beyond the WISER, this idea that we're using there in order to use ontologies as an entry point for integrating data. It clashes with one problem, and the problem is that in many applications we have to deal with streaming data. So this is because this is a streaming world. So in different kinds of scenarios, like in all operations, traffic, financial markets, and others, we have data that is produced in the forms of streams. And I guess this can also be the case in wind energy. And we find also this pattern in the web. Even if you think about social media like YouTube, Instagram, and so on, you have so many data that is produced every second, and this is what we call a stream, so data that is potentially infinite. And this brings us to the dimensions of big data, because we're maybe used to think that big data is just about the volume, how many gigabytes or petabytes or terabytes of data we have, but this is not the only thing that we need to care about. We also need to care about velocity, and this is especially important for streams. Data comes very fast. There are other dimensions like veracity and value of the data, but the one that is really, really complex more and more is the variety aspect. So the variety aspect means that we have data in many forms. Data is very heterogeneous, and we try, if we combine all these different dimensions of big data, then we have really big problems that are very challenging. In order to deal with volume, just with volume, how many petabytes of data we have different technologies that exist like MapReduce, etc. For velocity, when data is very fast, we have things like Storm, Kafka, Spark Streaming, different technologies that allow us to work with very rapidly changing data. However, in many and many kinds of use cases, like for example in oil operations or in smart cities, we have the combination of many of these things. So we have velocity and variety and volume at the same time. And when you have them at the same time, it becomes to be really problematic. But what are data streams anyway? So if we think informally or formally and informally, we can say that it's a continuous flow of information. So data that is potentially infinite, that is produced in a constant manner, and it's updated, like it can be every second, it can be every day. So the timeline or the time boundaries, they can be very different, but you have this sequencing and the order is very important. So usually the newer data becomes more important than the older data because it's more relevant, usually. Not always, but usually. And this also changes the way that we need to process the data. So we go from persistent data, so this is normal databases that are kind of static. You have a data set, maybe from a CSV or something. You can do machine learning on it. You can do different fancy things on it. But with streams, we have to deal with transient data. The data flows in some way. And as it becomes too fast to process, we need to apply this, for example, these ideas of windowing. For instance, let's take just the last 5 minutes of data and work just on that, because that's something that is more manageable. So these are the kinds of things that need a paradigmatic change. Instead of querying a data set, we need to have a query that is running all the time on the data and producing continuous results. So it's not just one query, one response, but it's a continuous query and continuous responses that are produced all the time. But it's hard to handle both volume and velocity. So this is a diagram where we see that if we have zettabytes and we have nanoscale production of data, then it really becomes harder and harder to process the data. And this is even worse if the variety variable comes in. If the data sources are very different, if the volume is very high and the velocity is also very high, then it's really more and more problematic to process all this data. And for the veracity aspect, the semantic web concepts, these ideas of using ontologies, it comes handy because it provides us this common way of modeling things that can be particularly useful. And the semantic web concept, it comes from the same concepts that have built the web as we know it. So the web that we use is a web of documents. So you have a web page that describes something, for example, a country, and then you have a link to another page that describes something that is linked to it. So we have this idea of hyperreferences and hyperlinks. So this is very nice for pages. It also works for images, so we can put images, videos, and different sorts of content, but all of these are documents. The evolution of the web goes into transforming this web of documents into a web of data. So instead of having just web pages, we have data that describes something. For example, we have the same information that in the web pages, but this is like data sets that are all over the web. And if you're familiar with the way in which this is structured, it is structured as triples. So triples is just these elements that have 3 elements: the subject, the predicate, and the object. So if we want to say, for instance, that Ireland has capital Dublin, this can be represented as this triple of information. And if we put as many triples as we want in a data set, we can have arbitrarily complex information in the form of a graph, because as you can very quickly and easily see, you can form big graphs out of these triple structures. So using this abstraction, people have built very big and interesting data sets. For example, from Wikipedia, there has been the construction of Wikidata, which is represents more or less the same information that you have in Wikipedia, but in a structured format, in this triple structure format. Also, Google, they have built their own knowledge graph that is structured in a very similar way. So you have facts that are structured in the web, and they use this in order to make their search engine more powerful, and so on and so forth. I can cite many examples where this idea of knowledge graph can really help structuring information in a way that is findable, but it's also connectable. We can connect different data sets because this notion of triples, it allows us to really integrate very different types of informations. So the principles for doing that are known as the linked data principles, which is put names to things, and the names are these uniform resource identifiers, so unique identifiers for everything. These unique identifiers are differentiable. We can get useful information out of them, and we can create links between each of them. So coming back to the problem of streams, how can we use these very nice linked data principles and concepts in order to link data streams? There are certain differences that we need to take into account. First is that we're talking about static versus streaming data. In the normal linked data setting, you have static data sets and you can create links with them. In the case of streams, this data changes over time, so it's not really the same. And the kinds of queries you can do to them are not the same. It's not a one-off query that I send a query and I get a response back. I have to do a query that runs all the time and produces results all the time. So this is a paradigmatic change. And I will show you in the next slides, in the rest of the presentation, how this can be implemented and how this has been done in the literature and in previous work. And this has been done in what we called RDF stream processing. So RDF is this model of triples. And what has been done is that we can create streams of RDF, a stream of these triples that can be queried, where you can really pose these queries and rules that run over time and that produce continuous results continuously, of course. So we keep the data moving. The data is not really static in any time. How do RDF streams look like? So they look like triples again. So you have all these triple structures over here that are kind of the same, but they are annotated with time. So you see there that the time is important because time will allow us to say, for example, this fact comes after this fact, and we can make reasoning and we can make temporal assumptions and temporal queries about that. So we will see this later. This is very important. So we have these triples that can be thought in terms of time as well. But how is this coded? How is this implemented? How web standards are used in order to implement this idea? So this I will show you now. So in sensor data, where this idea was applied for the first time, you have lots of data sets. So I can talk a lot about, for example, environmental data. Environmental data where you have CSV files or Excel files or R files or all sorts of data sets that are around that talk about, for instance, the climate or about temperatures and humidities and these kind of things. So this sensor data, they exist. Sometimes they are published in the web, and in some cases they are even published as RDF. So RDF datasets are one of these bubbles. And there are examples like the link sensor dataset or the Met Office from the UK or the IMET from Spain that publish, for instance, sensor data about weather, and they put it available as linked data. But this is a static data. So if you look at one of these data sets, it's essentially zip files with like millions of triples that you can download, and then maybe you can do whatever you want with them. You can do some analysis and so on. But it's still not, this is not streams. So you download data and you do something with it. And if you look at the data that they have there, so this is not very easy to read, but I can help a bit. You will see that these are actually triple structures where you can find, for example, what is measured. Here I find that precipitation measurement. I find units. I found the value of the measurement. And I also find the ID of the sensor, for example, and also the time. So when exactly this was measured. So I find all this information in these triples. And but something that is not very clear is something things like the order, for example. We have the triples there, we have the data, but it's not clear what is the timestamp. So we have here a result time. So we can assume that this is the time where this item was read. So maybe we can assume that this is the timestamp, but this is not entirely clear. Sometimes there are multiple timestamps. Sometimes there is a readings timestamp. Sometimes there is also a last update timestamp, and there are different kinds of notions of time that can be attached. And sometimes it's not so clear which one really is the timestamp. Then we need to understand also what is the order of in the graph. If this observation comes before the other one, which one comes before? If we know which is the timestamp, then we can answer this question. Otherwise, it can be ambiguous. And also how we consume these files, how we process them, it's not so easy because as they are published now, it's zip files, so we have to save them somewhere and store them, and it's not really a stream per se. How can we change this? So what the first thing people have done in order to change this situation is to take these sources of data, like for example, this sensor data that I have just shown, and to transform them using some ad hoc scripts to transform them into RDF with timestamps, and then call an RDF stream processor so that it can do some querying, continuous querying over it and get some results. So this is the first thing that people have done to do these ad hoc transformations. But actually, it's not always the best idea to transform everything into RDF, because as you may imagine, this original representation, which is, for instance, a CSV, it can be optimized quite a lot. You can apply a lot of summarizing algorithms so that you can compress this information a lot, because there is a lot of regularity, a lot of repetitions, so you can do a lot of compression here. That sometimes, if you transform everything into triples, if you transform this into something that looks like an ontology-based data set, it will really grow in space too much, and it will not be super efficient. So it's not always the best idea to transform everything into RDF. So this is a kind of a big warning. Don't always transform everything into triples, because you can have problems of space and of computation and so on. So what people have also thought about is, why don't we keep the data as it is? Because it's very expensive as well to transform all the time data, even more if it's in a streaming fashion, into RDF. And why don't we keep the data as it is, but we kind of create a mapping from the original data into an RDF view? So this is what I try to show in this slide. So instead of doing this conversion to RDF that is done here in an ad hoc way, we can use mappings actually. So we use this mapping-based approach. We create some mappings that tell me from CSV you can represent the same information using an ontology, so using RDF, and these are configurable. These are configurable mappings that you could change if you, for example, if you change it into another data model, you can also change the mappings and have different sort of resulting RDF as a result. So how do these mappings look like? I will not go into the details. So this is one example of a mapping. So there are standards for doing mappings. One is called R2RML, where you can define how the URIs, how the identifiers of all your elements will look like. For example, if you want to create identifiers for your sensors, you can do something like this. If you want to put details about what type of data is being recorded in terms of an ontology, for example, here is NO2 gas emissions. And here you can also put some information about the sensor combined with the time where the recording was made. So all of this information you can input into the mapping, and you can create correspondences between the original data sets, if they are in CSV, in JSON, in XML, or other formats, and to see what would be the representation of that in RDF. And this can this could help you go to this kind of setting, to this kind of architecture. So this is a system that we created some years ago called Triple Wave, where you can actually have many types of streaming data services built into a system. So you can have, for example, RDF that already exists that you can streamize, so you can deliver as a stream so that clients can have access to these streams, or you can have access to different sorts of data sources like CSVs or JSON files and so on. And using these mappings that are standardized, you can create views over these streams in real time. So basically you can create these mappings that will allow you to look at the data as if it was RDF, while originally the data was stored and organized in some other way. So that's for Triple Wave. And now I want to talk a little bit more about the data modeling and how queries look like, because I haven't talked too much about that. So as I said, data items are structures as triples. For example, if I have a sensor that to sense where people are, for example, I can say detect that, for example, Alice is in the same room as Bob, so they are in the same place. So this could be a triple. So this is one triple. And we can also organize data not only as triples, but also we can put several triples inside one graph. For example, I can say that Alice posts a message. The message is about Bob, and the message says that they are both in the red room. So we can put different sorts of information grouped together in one graph. And we will see later why this is interesting. But let's just keep this idea of having these triples that we can put in a stream. If we don't have time annotations, if we don't have time annotations, still, if we at least have the order of the triples, we can do some queries that are interesting. Let's say that I have this stream where I have a triple that says that Alice is with Bob. Afterwards, I have another one that says that Alice is with Carl, and so on. So we have this stream of different triples. Even if there is no time annotation, I still can, for example, ask if Alice met Bob before Carl. So Alice met Bob here, and he met Carl later. So we see that something happened after the other. So even if there is no explicit timestamp, we can still do some sort of queries. If we do have a timestamp, and we have the same triples, but we know that, for example, Alice met with Bob at time 1, she met with Carl at time 3, and then this happened at time 6 and time 9. I can do more complex queries. For example, I can ask how many people Alice met in the last 5 minutes. I can know if Diana met Bob and Carl within the last 5 minutes, and so on. So I can do this kind of more advanced queries. And if the model is even more complex, I can even create not point-in-time events, but I can create events that work in an interval. For instance, I can say that Alice is with Bob from time 1 to time 5, or that Alice is with Carl from time 3 to time 7, and so on and so forth. So with this, I can do even more interesting queries, like asking which are the meetings that last less than 5 minutes, because I can have this information, or I can know which are the meetings that have conflicts. So here we see that these two meetings, they have a conflict. So this is an introduction of what we can do in terms of temporal logics with streams. It's more complicated, but it's more powerful in terms of what kind of queries we can do. We have actually worked in trying to standardize these models, and there was a first attempt. I was the chair of the W3C group working on this task, and we came up with this model where you could, in graphs, you could put different triples, and in these triples you could put time properties, and this was RDF compliant, so you didn't need to have a new parser in order to read these data sets. And the metadata was also flexible. So the different features that made this attempt of standardizing this interesting. And we also allowed for intervals if it was needed. So as you see, many of these ideas, they they went to a path towards standardization, although it's still not completed at the moment. And from this modeling and from these querying ideas, there have also been implementations of these systems. So implementations of systems that go from the traditional, so this is the traditional way of doing queries over RDF data. So you have a graph store, a triple store here, you send a query and you get triples as results. So this is the standard way of working. While in RDF stream graph processing, we have this stream processor where you register a query, and this query is producing data from the data that is fed, and is producing continuous results as an answer. So you have continuous data that is produced as well. So there are many implementations of this, so I can mention briefly how some of them work. So for the next examples, the assumption is that we work with point-in-time semantics, so we don't have intervals here. So an event happens at a specific point in time. And the normal way of implementing queries with this kind of approach is that you have windows. And typically these are sliding windows. So if you have different events that are happening in your stream, then you can create a window of a length. So you decide which is the width or the length of your window. And everything that falls within this window will be included in the processing. So at this particular time, I will only process these 3 elements which are in my window. So this is
Jean-Paul,
the...
no, just quickly, I don't want to interrupt. I just want to tell you it's 10 to 4. Huh? I don't want to interrupt you. I want to have some time for questions. If you can, I don't know how you want to do it, but if you can sort of maybe come to a close until
I will. So I will skip some things and then we. Yeah, you're right. Time flies. So I guess you see the concept of windows, and we have also other different types of operators. So if you have the slides afterwards, then you can take a look at that. And there have been implementations of that. Some of them have been done by us. Some have been performed by other groups. So basically from a normal query of a knowledge graph, you add these window operators that you see here. And from this, you can do this sort of operations over the knowledge graphs and get results back. So the next slides, they go more into details of how this works internally. But for the interest of time, I can let you this for further reading afterwards. And maybe I can just jump down to the conclusions, which is just challenges. The challenges is that although we have this very nice way of working with streams, there's also the problem of defining these ontologies, which are domain specific. So in your domain of expertise, defining these ontologies community work, and this is something hard, especially because reuse of the ontologies is not straightforward. Everybody wants to do its own thing, or his or her own thing. Also, reasoning using ontologies is more difficult when streaming data is in place, so as you could have imagined. So there are lots of works that have been done. I have right now a Swiss National Science Foundation just dedicated to this problem right now that is starting next year. There's also the question of combining machine learning and reasoning based on ontologies. So this can be very powerful because we can have reasoning based in ontology-based data and also based on data itself. So the combination of both is something that is really promising. And another challenge is fair metadata management for streams. So even if your streams come in format that has nothing to do with ontologies or with RDF, you can still just represent the metadata of the streams using ontologies, and this can already be something very interesting in order to allow discovery and integration of your streaming data. And the final consideration is data delivery that can be negotiated. This is especially interesting when you have different servers that deliver streaming data and you want them to cooperate. So there are notions of agent-based negotiation that you could use in order to synchronize or to create cooperative streaming data processors. So I guess I took a little bit more time than expected, but I hope you found something useful in this presentation. And if you have questions, I'm there for answering.
If Yeah, really interesting. Thank you. And I very much appreciate the last slide of challenges as well. I think that's useful for all of us. So questions. We have 7 minutes. Anyone?
So I do have a question. Yeah, again, thank you for the presentation. I really wish I had access to these kind of presentations when I was starting. It would have directed me much faster, probably, to the things I had to learn while going through it. One question in it I had is what role do closed world validation schemas are playing in this, in terms of like JSON schema, like validating the data, streams maybe on the input? Are they playing any significant role? Do they fit into this architecture?
Yeah, that's something that I mean, that's actually also a challenge, because most of the ontology schema validation works have been done on static data, so data that doesn't change as fast or as dynamically as streams. So there is actually research work to do that, so that we can have, for example, shackle data validation with streams. And we can also do fancy validation. For example, we could validate if a certain type of observation happens within the last 5 minutes. So that could be a validation rule, actually. And this is something that is not considered in the shackle or checks. If you're familiar with the data validation technologies, it's actually not considered yet. But that's that's subject for research, actually.
Perfect. And that's what we need.
That's what we want. The thing that I was thinking of when you were showing the challenges screen is if, like, in wind energy, we're not as far as you are at all. So this whole thing about streaming is really interesting, but we need to have a first step with static data. But my question would be, if we're designing some sort of domain-specific ontology, is it important to take account of the fact that you might want to have one for streaming later in the future, or is the streaming part like an add-on thing that it doesn't matter, you don't have to consider it at the beginning? Do you understand what I mean?
Yeah, I think usually, at least in the use cases I've worked with, you can start working with the data catalogs first. So this is not streaming data. So this is identifying first which are your data sets, what characteristics they have, etc., etc. So all of this can be modeled using ontologies, using extensions of existing ontologies. And in a second step, you can attack the streaming data. So I don't think you necessarily have to spend so much time in the streaming part if you start at least with the data catalog part. At least that's also what we're doing in the WISER project with sustainability. We are not dealing so much with the streams right now. It's again, it's working first with the data catalogs at the beginning.
Yeah, okay, good to know. Anything else?
May I ask a question? First of all, thanks a lot for a very interesting presentation, and it's quite a lot of new stuff for me to digest, but definitely super interesting. One just kind of spontaneous thought I had, and I thought I would ask what you think about it, is that it's a kind of general challenge around machine learning is kind of integrating it with domain-specific engineering knowledge. I think there's a lot of machine learning approaches that just take a pure data approach and kind of throw away all the domain-specific knowledge. And do you think this framework could help to? I think that's kind of maybe what you're alluding to, but I thought it'd be interesting to hear your thoughts on that. If this framework could be useful to combine domain-specific kind of knowledge experience with machine learning approaches.
Mm.
Yes, we think that one of the potential advantages of doing this combination is that you could get explainability to a large degree. So one of the problems in many scenarios, I mean, I work a lot in the health domain, is that many of the results that you have are not explainable or explicable or understandable even with pure machine learning. And if you have this combination with the domain knowledge, then you can really get to this point. So I could talk about embeddings of knowledge graphs that can be used for machine learning. So this is one of the ways of integrating this knowledge into a machine learning process. And this is something that that can help with the explainability part. And in some use cases, I don't know for wind energy, but it can be really key and sometimes a key requirement actually.
Right, thank you.
Yeah, sounds interesting.
Yeah, it's definitely a subject of a research. It can be definitely applied in like structural health monitoring, and integrating domain knowledge with machine learning is definitely one of the interesting directions. So thank you for the good question.
Yeah, I mean, I think
yeah,
go on.
Sorry, I interrupted. No, I was just saying in terms of streaming, I suppose one use case would be kind of failure detection and so on. If you're kind of continuously getting lots of CMS, the condition monitoring data from kind of high frequency vibration sensors and stuff like that on the turbines, and also SCADA data, and you've got lots of data sources continuously coming, and ideally if anything goes wrong, you want to pick up on it as soon as possible, that you can do something before something serious breaks.
Yeah. Okay, it's 4 o'clock. My next meeting's already started. I just want to let you know I put the 2 links in the chat. The first one was just to the We Do Wind ecosystem, and you can have a look at what that is, because what you can do is you can see things like fault detection. You can join We Do Wind and actually work on some of the challenges regarding fault detection. But what you can also do is the second link is the one about the metadata challenge. Like if you want to talk about these issues in more detail with wind energy people at our monthly meetings, feel free to sign up for that space as well. Otherwise, just look out for the next invitations to our next. We're going to try and do a webinar once a month. We've already got quite a few lined up, so stay in touch. And yeah, if you sign up for the metadata challenge, you'll get automatic updates as well. So yeah, thanks. And then thanks to Jean-Paul for his very interesting presentation. I feel like, yeah, it could have gone on for a long time. It wasn't because I was getting bored that I asked you to stop. I think it was really, really useful. And yeah, let's keep talking about these things and keep in touch, and hope we can collaborate in the future. So if anyone's got any more questions, sign up for We Do Wind and write it down in the forum there, or send some direct emails, or you can even write in this chat after the event stopped. Actually, I see Stephen's writing something. I don't know whether he's just writing bye or he wants to actually ask a question. Oh yeah, okay, great. All right, thanks everyone.
Thank you.
Good afternoon. See you soon.
Bye.
Bye.
Thank you.
Bye.
Bye.
Bye. Thank you.